Good evening. My name is Sho Yokoi from Kobe University. My presentation is impedance-tuned ultrasound vibration wireless power transport system for biomedical devices. The outline of this research as a part of development of WPT technology for medical use using ultrasonic vibration. In this research, we purpose ultrasonic WPT system, UWPT, that incorporate a resonant tank to improve the output power and power supply efficiency, and the structure of equivalent circuit of the UWPT module is determined. Finally, maximum output power of 260 milliwatt and maximum power transfer efficiency of 9.6% are recorded on the experimental verification. This is a table of contents for this presentation. First of all, I will explain the background and purpose of my research. The purpose of this research is to develop medical WPT technology using ultrasonic vibration, which is a non-invasive and non-contact technology for powering medical devices built into the human body. There are three technological backgrounds to this research. This technology can also be applied to various medical devices built into the human body, such as a pacemaker, capsule endoscope, and cochlear implant. That is the chart comparing the method of the powering medical devices. The currently used method of replacement surgery involves risk dwelling surgery and economic risks and is highly invasive. The WPT method has not yet been put to practical use, but is known to reduce the risk significantly compared to surgery method. There are two types of WPT method: the magnetic resonance method, IWPT, and the electrical coupling method, CWPT. However, high frequency induction current heating and metal plate heating have an effect on the human body. On the other hand, UWPT expected to be put to practical use as a means of supplying power to medical devices. The reason for this that is there is no health hazard, and it can be developed into bioenvironmental power generation. This figure shows comparison of power transmission distance and output range of each WPT method. The IWPT and CWPT methods are capable of outputting power over wide range and relatively short distance. This is method used for industrial application. On the other hand, WPT has advantages, longer power transmission distance than other methods, but due to sound attenuation caused by obstacles such as skeletons, the power range is generally low, and the power transmission efficiency is low. Because of this, current application of UWPT is quite limited. In this study, we purpose resonant UWPT system that incorporate a new resonant tank as a countermeasure. A goal of this research is to increase this output power and efficiency of the system and to expand the application of UWPT. Next, let's move on to the explanation of resonant UWPT system. This is schematic diagram of proposed UWPT system. The ultrasonic phantom in the middle is like internal tissue of the human body. The system uses piezoelectronic transducer PTs, PTs positive and negative piezoelectronic effect to supply power from outside the body to inside the body. The resonant tank installed on the transmission side and receiving side plays the role of power compensation and waveform improvement. The circuit configuration of UWPT system is described in detail in the following section. This is the circuit diagram of resonant UWPT system. In order to reduce the size of RX circuit, resonance tank installed on the TX and RX sides are lumped together and installed on TX side. Impedance matching network is installed between the resonance tank and TXPT to adjust the sharpness of resonance cube. In order to design a resonance tank, it is necessary to estimate the impedance of TX and RX PTs, including the phantom. The PT, including the phantom, is called the UWPT module. On the other hand, At the Rx side, voltage doubler is applied to boost the small voltage generated at the Rx-PT. I will continue with explanation of the URPT module equivalent circuit. The upper circuit is the equivalent circuit of PT, and the force coefficient A is the convention coefficient between electrical and mechanical system, and it represents the ratio of the compensation between electrical and mechanical parameters, just like the ratio of number of turns in transformer in electrical engineering. The PT equivalent circuit, in the PT equivalent circuit, electrical and mechanical parameters are mixed together. The electrical parameter can be measured with laboratory equipment, but the mechanical parameters are very difficult to measure and calculate. So mechanical parameters are combined to electrical parameter as shown in equation 1, 2, 3. The equivalent circuit of investing tissue between the PTs in the URPT module can be represented by the zigzag circuit as shown in the phantom part of the figure below. Based on above process, the equivalent circuit of URPT module can be expressed as shown in the figure below. Using equivalent circuit of the TX and RTX PT is shown on both sides, and the equivalent circuit of the phantom section. The parameter of zigzag circuit in the phantom part can be defined by the equation on the right. Among them, epsilon RT and gamma T vary greatly depending on the frequency band, which makes it difficult to derive and analyze them with high accuracy. From the above point of view, the above later type zigzag circuit can be transformed into the simple T-sharp equivalent circuit as shown in below. The impedance of T-sharp circuit can be expressed by the equation below. The above figure shows the equivalent circuit of URPT module when the phantom part is represented by a T-sharp circuit. However, even at this stage, it is difficult to derive and analyze parameters with high accuracy due to large number of circuit parameters. Therefore, the series and parallel component in this circuit and lumped together and replace it by Z1 dot and Z2 dot to convert equivalent circuit of URPT module into a simplified L-sharp equivalent circuit shown below. And by measuring impedance characteristics by shorting and opening the terminal 2 to 4 of the module, the lump parameter and derive it to construct the equivalent circuit of the URPT module. The figure on left shows the impedance measurement system configuration. A broad rangeband transformer BLT capable of emitting hyper ultrasonic vibration is used as a TX and RTX PT. This enables URPT system to have high power. The URPT module is constructed by inserting an ultrasonic phantom between the TX and RTX BLTs. Next, we will discuss the measuring results. The figure shows the impedance characteristics of the URPT module when the terminal pair 2-4 is shorted. The point to be noted here is frequency band where the impedance becomes minimal. With this in mind, let's take a look at this picture. Minimal impedance at a frequency of about 39.3 kHz, and the changes in impedance and phase are gentle. Therefore, measuring the impedance in this frequency band and constructing the equivalent circuit of the module, the losses inside the module can be minimized and the URPT system can be operated efficiently. And in addition, the gentle changes in impedance and phases makes it possible to control the frequency easily. The impedance characteristics of the open circuit also show that impedance is minimized at 39.3 kHz. Since both phases are capacitive both phases are capacitive, Z1 dot and Z2 dot in the L-type simple equivalent circuit of the module shown earlier can be expressed in terms of capacitor and resistance components. Therefore, based on results on so far, the equivalent circuit when terminals 2, 4 are shorted and opened is as shown in the middle figure. From this figure, the impedance seen from an internal pair 1, 3, terminal pair 1, 3 side when short circuit can be expressed as equation 10. The impedance when open can be expressed as equation 11. For these two equations and experimental results, parameter of L-type equivalent circuit of UWT module can be obtained as shown below. From the above, the process, it is possible to design a series resonant tank by giving value of Q, sharpness of loading resonance. Let's move on explanation of the experimental verification. First of all, I will explain the mentioned items. After measuring P1, P2, and P3, the inverter efficiency, eta1, power transmission efficiency between PTs, eta2, and system efficiency, eta3 are calculated. By calculating these three efficiency, it is clarified in which part of the circuit the losses in occurring. Lower part is a circuit parameter, and the effectiveness of the design resonant tank is discussed by looking at the operating waveform. There are waveforms of the voltage and current between terminals AV and the voltage and current of the TXPT. It can be seen that VAB and IAB are almost in phase due to effect of the series resonant tanks LS and CS, and IPT1 is resonant waveform. These results show that the equivalent circuit of UWT module and the operating frequency design of inverter are correct. Next, discussing result of each efficiency mentioned. System efficiency frequently greatly over time. 30 seconds after startup of the prototype, the maximum system efficiency of 9.6% is recorded and the output of 260 milliwatt. And after 1 minute, the system efficiency stabilizes at 1.9% at 30 milliwatt output. In addition, in both cases, maximum efficiency, stable system efficiency, eta2 is extremely low compared to inverter efficiency. This indicates that there is a large losses between the TX and RTXPT that is within the UWT module. And finally, I will summarize my presentation and describe now future research work. In this presentation, the equivalent circuit of UWT module was first constructed to drive the circuit parameters, and then design tank was designed. Finally, experimental verification revealed the usefulness of the designed resonant tank. As a result, maximum output power of 260 milliwatt and system efficiency of 9.6% was recorded, but the losses inside the module were found to be large. The tissue of UWT system currently under the construction as follows. Increase in the size of TX side circuit due to an installation of MT on TX side, difficult to implant the BLT used as a RTXPT in the body at the RX side. In the UWT module, they describe in system efficiency due to large internal losses in the UWT module is mentioned. In this study, we plan to reduce the size of TX side circuit by constructing an empty-less impedance matching network, and to reduce the size of RX side circuit and the internal losses in the module by using small medical PZT in the place of BAT. This is end of presentation. Thank you very much for your attention.